meta-analysis in R statistics with a binary outcome based on the effect size, which is the odds ratio, to generate a forest plot and a funnel plot. Binary outcome is a variable that is categorical, a variable that have two levels in it, such as alive or dead, yes or no, smoke, doesn't smoke, have disease or doesn't have a disease. Meta-analysis is a statistical method that combine and summarize results from several independent research studies. The objective of meta-analysis is to calculate the overall estimate of effect size for specific exposure by pooling results from several independent studies that addresses the same scientific medical research question. The meta-analysis also will examine and assess the degree of variability and inconsistency in the results among these several independent studies by performing a heterogeneity test and generating an I-squared value, which is represented in a percentage. 0% indicates no heterogeneity, and 100% I-squared represent maximum heterogeneity. The meta-analysis statistical method will also generate a forest plot. So what is a forest plot? It is a diagram or a graph that displays the outcome or the summary of the meta-analysis. The graph will display the summary for the single specific effect size, estimate for each study, the 95% confidence interval, p-value, weighted percentage, and the graph or the plot itself consists of three main sections. The first section is descriptive statistics. The second section is a diagrammatic reflection or representation of the statistical description, and a third part or section describes the overall effect size and the test of homogeneity or heterogeneity with an I-squared values and p-value calculated. Meta-analysis also will produce a funnel plot. A funnel plot is a graph that displays on the x-axis the estimate or the effect size estimate for each individual study, plotted against the y-axis, which is have on it the standard error or the sample size. The objective of the funnel plot generation is to assess any bias in the publication. To perform meta-analysis for a binary outcome based on effect size, which is the odds ratio, in R statistics, launch the R Studio and then load the file that have the data. And the way to do that is to click on file and then select import data set, and since the file is stored in an SPS format, then select from SPSS, and in the new window here click on browse, select the file that contains the data for meta-analysis, click on it, and it will be loaded into the R Studio as shown here, and then if you take on import, it will be loaded into the R Studio. And as shown here in the table, there are 12 studies as shown in the left column for the study ID, 12 independent studies, and there are 2 groups in each study. So the participant has been organized into an experimental group for abbreviated E, and a control group which is C. So here a drug is administered to 2 groups. One is given the drug, the other one is a control that is given a placebo, and the success rate of recovery from the condition is recorded, and a score is given by an event. So those who succeeded in recovering from the condition are scored, and a column is, or a variable is generated called event in the experiment, and then the total participant in the experimental group is given here, and the event occurring in the control group without intervention is also recorded and inserted in the variable called event in the control, and the total number of participants in the control group is recorded. So there are 2 groups in each study, and the objective is to do meta-analysis on these data from these 12 studies. And since the outcome here is binary, whether the event has occurred or the event has not occurred, whether the participant has recovered from the condition or not, so it's a binary outcome, then the effect size measured or estimated here will be the odds ratio. And the way to do binary outcome meta-analysis in R statistics is first to install the meta package and then load the meta package into the R statistics. So we'll type here in this section library. I had already installed the package, so I'm going just to load that, and if I hit enter it will be loaded. The next step is to use a certain command to perform meta-analysis. Let's first generate an object, call it X, and use the assignment operator, and then type in the command or the function for the meta-analysis, which is meta pen for binary, and that is the function is already installed there. Open a bracket, and within the bracket, after the first bracket, type in the data name equal sign, and then the data file or name is already generated here, so I'm going to copy and paste that to here. And to continue with the command for meta-analysis for binary outcome, we had inserted the data label or the data name. The next is to insert the variable for the event in the experimental, which is event case sensitive E, event E, and then comma, and then the total number of participants in the experimental group. So total, it has to be capital, total dot E, and For now, this is for the experimental group. So we have the first variable, which is event, then the second variable, which is the total. And for the control group also, event here has to be capital letter, as R is case sensitive. Then we need to insert the event dot c, comma. So this is the third variable that have the event scores for the control, and then the total number of participants in the control group, and that is total dot c. Then we need also to choose the effect model, which I'm going to use the random effects model. So I'm going to type random equal to true, and then for the fixed equal to false. So here I am selecting a random effects model. If I want a fixed effect model, then I will give the fixed true and the random F for false. After that, insert a comma and then choose the method to perform the meta-analysis by typing method equal sign, and I'm going to use the MH method, which is the Mantel-Haenszel method, then followed by a comma. And for the summary of the result, I'm going to type SM, then equal, open a bracket, and I'm going to use the effect size, which is the odd or odds ratio. We could use risk ratio, risk differences, and so on. Then insert a comma, and I'm going also to insert the study labels, which is the first column, by typing stud label or study label, and then open a bracket, and then I'm going to select the variable, which is study ID. So this will select the study ID variable. So this is the command or the function for performing binary meta-analysis through typing the command metapin and the data, the name of the object created, which is the data, the event in the experimental, the total in the experimental, the event in the control, the total in the control, and choosing random effect models, and then the method MH and the summary OR, odds ratio, and inserting the study label or study ID. Just drag this bracket to here, and then click on enter. To view the output, just type X and then insert as shown here. The output shows that the number of studies K equal to 12 studies, since we have 12 studies, and the number of observation is 1633, and the number of events occurring, which is E, 741. And the next line is showing the random effects model with an OR and a 95% confidence interval, and a p-value is generated here. And also a heterogeneity test is performed and quantified using tau squared, and a value is given with a 95% confidence interval, and an I squared also given in a percentage with the 95% confidence interval as shown here, and the test of heterogeneity with a degree of freedom given here 11, and a p value, and the q which is based on the chi-square. So from this heterogeneity test, it is shown that there are 0% of heterogeneity, as the I squared equal to 0%, and the p-value is greater than 0.05. We need this p-value to be greater than 0.05. So this output or test of heterogeneity showed that there is no heterogeneity among the results from those 12 studies. To draw a forest plot, just type forest, then open a bracket, and let's insert an X, which is the object that we had created, and then a forest plot is generated as shown here. Shows in this forest plot the study ID, the event, experimental control, events and total for experimental and control, a diagrammatic representation with the odds ratio, and the 95% confidence interval, and the weight and the scale here. To redraw this in a RevMan format, just type forest, open a bracket, then X, which is the name of the object created, and then type layout, open a bracket and or quotation mark, and type RevMan. So this will produce the forest plot in a RevMan format as shown here. This is for RevMan. The studies from 1 to 12, the diagrammatic representation is on the right hand side, the odds ratio is given, the MH method, and a random effect model is used, and the odds ratio event in each group. If we close that, back again to the forest, and I'm not going to use the RevMan, I'm just going to use a forest plot that is standard, and I'm going to edit part in it. So type forest, and then open a bracket X, and then I'm going to add a pooled. So if we just hit the enter and look at the forest plot here, there are few missing values. So the value for the event for the experimental control is not given here, and I'm going to insert that, and I'm going to give a plot which is an X label by calling it, let's say drug A. So close that one, and then type forest again, open a bracket X, and to insert the event for the experimental and the control, type pooled dot event, and then equal true, then comma, and if you just hit enter and look at the graph here, the forest plot, we can see that the event, total event for experimental and for control is inserted here. Close the plot window, and I'm going to give the x-axis a label. So we type here forest, then x, and then copy the same thing as the pooled. Here we need the pooled event, pooled events, and then comma, and I'm going to label the x-axis by typing xlab equal to, let's call it drug A, space drug A, and hit enter. Click on the zoom, and as shown here, the plot is given a x-axis label which is drug A. To do a few editing on the plot here, close the plot, and again select the command here, insert, and then after the drug insert a comma, and then to change the color of the squares in the diagram, type color, and then select a square, which is this one, color of the squares, and then open a bracket and or quotation mark and type red and hit enter. Red is misspelled. Then let's select the command again, copy, and then insert that here and correct that into red and hit enter, and then click on zoom. As shown in the plot here, the squares for the effect size or the odds ratio are color coded red. To change the diamond color here, or the diamond shaped, which is the overall effect size, into a black color, close the window, again copy the command for the forest plot, and then after the red type color, and then diamond, select the diamond function, and then open a bracket and let's give it a black color and hit enter. And if we click on zoom, the diamond shaped now is colored black. So looking at this forest plot, it consists of 3 sections. The first section is a descriptive. The second section is a diagrammatic representation, and the third section here, which is the heterogeneity test and the overall effect size. The first column here is the study ID from study 1 to study 12. The second one is experimental, as shown here, the data for the experimental group and the control group, the events in the experiment and the total in the experimental, and the same for the control for each individual study. And if we scroll down to the end here, it shows that the random effect models with the values for all these columns. And on the right hand section here, it shows that the effect size is the OR, which is the odds ratio for each individual study, with a 95% confidence interval for that OR, and a weighted percentage, which reflects the impact or the influence of the sample size on the meta-analysis. And at the end here shows that the overall odds ratio for all these 12 studies and the 95% confidence interval. And here is the scale or the ruler from 0.01 up to 100. And in the diagram here, the red squares represent the odds ratio for each individual study, and the size of that square reflects the size of the samples or the number of participants recruited for each study. A higher sample size will have a higher size of a square. The horizontal line represents the 95% confidence interval for each individual study, and the vertical dashed line represent the pooled odds ratio or the overall odds ratio. In the section here also, heterogeneity test has been performed, an I-square is generated and a p-value is generated, and the I-squared is equal to 0% and the p-value is greater than 0.05, which indicates that there is no heterogeneity between the data extracted from all the studies. So this is the way to produce a forest plot. Now to generate a funnel plot, close this window, and in the section here type funnel, and then open a bracket and put X and then hit enter, and then click on zoom, As shown here in this plot, this is the funnel plot as it is in a shape of a funnel, and on the x-axis is the odds ratio for each individual study, and on the y-axis is the standard error. The objective of drawing funnel plot is to determine whether there is a bias in publication or not. For no bias in publication, the distribution of the effect size should be evenly located above and below this middle line here, which is a vertical line, and this represents the overall odds ratio. So the odds ratio for each individual study have to be equally distributed in the both side of this line. From this funnel plot, we have 1, 2, 3, 4, 5, 6, 7 on the right side of the line or above the line, and 5 below the line. So there is bias of publication from this funnel, and another test need to be performed, which is Eager's regression test, to confirm that bias does exist. So this is the way to perform binary outcome meta-analysis in R statistics based on the odds ratio to generate forest plot and funnel plot.